Hey all, so we're going to keep talking about a couple more tests for convergence, and we're going to talk about three ones pretty quickly, but they are relatively basic. They're not adding in anything super new, but do get yourself ready for notes, and we're going to talk about the comparison test, and then we're going to do a brief sidetrack on something called pSeries. So here we're looking at some series. Determine if 1 over 2 to the n plus n converges. And so what I would hope that this makes you think is, one, I don't want to use the integral test because integrating this is not going to be cute. It can't use partial fractions for it. It's not like a trig inverse, which sometimes we want to think about with 1 over fractions. But what we can use is what's called the comparison test. So the idea here is that if I have two series, one that's A and one that's B, with positive terms, where A is always bigger than B. And so it could be positive terms. It could be all negative terms, as long as it's consistent. Because the idea with positive is like if it's negative, factor out the negative from both. And the idea is that if A is always bigger than B, that means if B diverges, if B goes towards infinity, well, A is bigger, so it will also diverge. Whereas if A converges, so if the bigger one goes to 0 and goes to a number, then the little one also has to go to the number. So it's sort of it's like a mix between the sandwich theorem, right? If we're thinking about it in terms of a curve, if the bigger one grows without bound, if the smaller one grows without bound, the bigger one has to go even bigger. On the other hand, if the larger one goes to a number, then the smaller one has to also go to a number because it's in between them. So if thinking about the sandwich theorem makes sense, that's helpful. So in this case, we're going to look at this complicated function, and we want to say, oh, what do we want to compare this to? And what you're often going to find is you're just going to look at it and say, oh, I recognize part of this. So when we think about series, you're often going to recognize geometric series in here. And you're going to say, okay, well, I'm going to compare this to 1 over 2 to the n. Because it's got the plus n, but, you're like, okay, well, let's ask ourselves the question. So if I have 1 over 2 to the n, this is always going to be greater than, so this becomes the question then, what's the inequality? This is going to be greater than 1 over 2 to the n plus n because this one has a larger denominator. And if you have a bigger denominator and same numerator, you're like, okay, well, if that's the same numerator, but the denominator is bigger, that means that the fraction is a smaller number, right? 1/3 is smaller than 1/2. So then the question is, does this one that we're comparing to converge or not? Now 1 over 2 to the n, that looks more like an exponent. This is the same as 1 over 2 to the n, since 1 to the n is 1 no matter what. So then this would be a geometric where r is equal to 1/2, which means that it converges. Since 1/2 is less than 1 and it's positive. So what that means is that the larger term here converges. And so since the series 1 over 2 to the n from n equals 1 to infinity converges, then the series from 1 to infinity of 1 over 2 to the n plus n also converges. So just comparing it. Now you can also use the limit comparison test. You can use either. The limit comparison test is basically the comparison test with easier algebra. So, and what I recommend that for is problems like this where you have a fraction that's got a lot of terms in it that's like a polynomial. I recommend the limit comparison test for those. So again, you're going to say, all right, well, if there's two of these, if there's two series, A and B, and A is the bigger one, if the fraction of a over b, so again, a is the bigger one, is equal to a constant that is greater than 0, then either they both converge or they both diverge. So basically what this means is that if it's equal to a positive constant, their behavior is the same. So, right, same idea here. Their behavior is the same. They want to match. Now, when we look here, when we talk about what we want to compare it to, for the limit comparison test, I generally just want to compare it to a similar one. So I'm going to say, but that's more simplified. So 2n squared over root, and then instead of n squared, I'm going to go with n to the third. And the reason for that is, I know this has plus 5, but remember, I want to be able to do an easier comparison like this. So I still want, in this case, I'm going to have a bigger denominator. So just like what we saw in number 1, and since I took away 3n, then I have a smaller numerator. So sometimes you change both. And what this means is that this fraction is going to be less than the original. So if you could also just use the straight up comparison test here, which is what I am actually going to do, right? Because I have to find that just making the change I want here so that I know what's true is easier. So then I'm asking myself 2n over root n to the third. This simplifies to 2n squared over n root n. We could also write it like this. That's 2 to the root, 2 times root n. Now, since this is less than our series that we're given, so a is the bigger one. Now the question is 2 root n convergent? And no, because we can use the limit test. The nth root test is what the AP calls it. And that just means, okay, well, what happens as n approaches infinity of 2 root n? Well, that's just 2 times infinity. That's infinity, which means that this is divergent, which means a n is also divergent because they have the same behavior. Now, what's going to be helpful here is that this is going, anything that's a power, we call this a pSeries, but that's just n to a power. So whenever we're talking about a polynomial in series, as long as p is less than -1, it's going to converge. The alternative way that this would be written is that the series 1 over n to the p converges if p is greater than 1. So sometimes it's easier to think about it as a fraction, sometimes it's easier to think about it as a power. And so here, when we do our comparison test, like we're looking at number 3, 5 over 2n squared plus 4n plus 3, I'm going to compare. And again, I'm going to compare to a simplified version, which would be 2n squared. And what we know is that that is going to be bigger than my original, since again, my original has a larger denominator. It's got things added to it, like so. Now, this is a p-series, so 5 over 2n squared. The series of that is 5 over 2, and you can either think about it as 1 over n squared, where p is greater than 1, or it would mean that the power is -2, which is less than 1. So here we know that this converges by the p-series test. So since the larger one converges, that means that my original series here also is convergent. So you'll notice here I didn't actually use this limit comparison test in either of them. I just find it easier to create one to compare it to and use my logical thinking skills with either an integral test that I recognize or a pSeries that I recognize. You can do you can look at some examples of those. If you're interested in examples of those, please get in touch with me. Otherwise, most of these I find it's more straightforward and faster, and especially because the AP is a time test, faster for the few times this problem comes up. Just ask yourself, okay, what's this the most similar to? Does it look like a geometric? Does it look like a pSeries? Does it look like one of the integral ones that I recognize, such as tan inverse, which is a really common one? If you have questions about these three problems or these tests, please get in touch and leave me any note in the comments that you like. If you're stuck on a homework problem, please nominate it. And remember to turn in the review assignments. Those are assignments where something is due.